Earth occupies a distinct position as the third planet from the Sun, sitting at an average distance of approximately 150 million kilometers, a measurement we define as 1 astronomical unit. Curious, instructive, this map of the inner solar system shows the circumstellar habitable zone. This is the precise region around a star where atmospheric pressure and solar radiation allow liquid water to pool and remain stable on a rocky surface. Venus and Mars sit roughly at the inner and outer edges of those boundaries, despite sharing our exact same origin point and basic chemical precursors. Venus sits slightly closer to the Sun. Early in its history, surface temperatures exceeded the threshold for liquid water, causing its primordial oceans to evaporate entirely. That water vapor trapped incoming heat, triggering a runaway greenhouse effect that boiled the planet dry and left it locked beneath 92 atmospheres of crushing pressure. Mars cooled too rapidly because it possesses only about 10% of Earth's mass. As its internal core quickly solidified, the planet lost the ability to generate a global magnetic field. Without that protection, the solar wind stripped its atmosphere away to space, freezing the surface into a barren, dusty wasteland. Being at the right distance from the Sun does not guarantee a temperate climate. Earth has maintained liquid oceans for 3.8 billion years because it operates a complex, continuously active internal engine that our neighbors lost. Our atmosphere is a highly stratified thermal system that precisely regulates the planetary energy budget. This cross-section shows the lowest 12 kilometers of our sky, known as the troposphere. At the very top of this layer sits the tropopause, a physical boundary that acts as a cold trap. When rising water vapor hits this boundary, the sudden temperature shift forces it to condense and fall back to the surface as rain or snow, preventing our moisture from floating into the upper atmosphere. The Sun continuously blasts out a high-speed stream of charged plasma known as the solar wind. If those particles collided directly with our upper atmosphere, they would break apart vulnerable molecules like water vapor and permanently scatter them into the vacuum of space. The defense against that constant solar erosion is generated roughly 3,000 kilometers beneath our feet. Inside the liquid outer core, a massive ocean of molten iron and nickel undergoes vigorous convection, heated by the solid inner core below it. As Earth rotates, this churning metal creates intense electrical currents, which generate an enormous magnetic field known as the geodynamo. That magnetic field extends thousands of kilometers into space, forming a teardrop-shaped shield called the magnetosphere that safely deflects the solar wind around the planet. Without the violent radioactive heat of the deep interior, the dynamo would stop churning, the magnetic shield would collapse, the solar wind would shred the cold trap, and our water would boil off into space. The heat radiating from the core also drives convection in the solid rock of the mantle, forcing the rigid tectonic plates on the surface to constantly shift and collide. This diagram illustrates tectonic subduction, the primary engine of the carbonate-silicate cycle. Rainwater washes carbon from surface rocks into the ocean, where marine organisms use it to build shells that eventually settle on the seafloor as limestone. As the oceanic crust slides under a continental plate, it drags those massive carbon deposits deep into the mantle. Deep underground, extreme pressure and heat convert that limestone back into carbon dioxide gas, which is eventually vented back into the atmosphere through volcanic eruptions. This constant recycling regulates atmospheric carbon, keeping global temperature stable. While volcanoes regulate the carbon, the global ocean manages the raw energy. The oceans contain roughly 97% of Earth's total water volume. Because liquid water has a remarkably high specific heat capacity, the ocean acts as a massive thermal buffer. It absorbs roughly 90% of the excess heat trapped by greenhouse gases, taking in vast amounts of energy with almost no change in temperature. This map shows the Atlantic meridional overturning circulation. Warm, salty surface water flows from the tropics up to the North Atlantic. There, it cools, sinks to the seafloor, and travels back south as a deep current. This physical distribution of energy prevents the equator from boiling and keeps the northern latitudes from freezing. Earth avoids a runaway greenhouse effect, because tectonic plates steadily recycle atmospheric carbon, while ocean currents relentlessly absorb and distribute the solar heat. The final requirement for this stable climate sits 380,000 kilometers away. Compared to other planetary satellites, our moon is unusually large relative to its host planet. The gravitational pull between the two bodies creates tidal bulges in our oceans. As Earth rotates through those bulges, the resulting friction acts as a braking mechanism that locks our planet's axial tilt precisely at 23.5 degrees. Without that lunar mass acting as an anchor, Earth's axis would wobble chaotically over geological time. The poles would frequently swing to face the sun directly, subjecting the planet to alternating periods of blistering, constant radiation and total darkness, shattering any chance for long-term ecological stability. Every piece of this planetary architecture depends completely on the others. Massive volumes of liquid water, for example, are required to lubricate the crust, keeping tectonic plates ductile enough to bend and sink into the mantle. This flowchart maps the sequence. Water lubricates tectonic plates. Tectonics vent mantle heat to sustain the liquid core. The core generates the magnetic field. The field shields the atmosphere, which maintains the pressure necessary to keep water liquid. Earth is a highly integrated, self-regulating machine. It continues to harbor life precisely through the endless, synchronized movement of heat, rock, and water against the vacuum of space.